Enthalpies, entropies, and Gibbs-free energy. It could be treated by Hess's law. Hess's law, the main idea of it, some reactions is carried out by using multi-steps, 2, 3 or more steps, so that you may extract target reaction in order to calculate the heat of this reaction by referring to multi-steps here, but just modify those equations by multiply it, by divide it, by flip it in a certain way, applying the concepts of chemistry. For example, we said that, for example, Na plus Cl2 produce NaCl. If you want to balance it, in general, we said that 2 here, 2 there, and it's balanced. Also, you may multiply the whole equation here by any factor like 5 is turned to 10 Na plus 5 Cl2, 10 NaCl. So, the chemical equation, it simply could be treated like a mathematical equation, and that's the first fact. The another fact, you may flip the direction of reaction, product turns to reactant, but keep it in your mind, you're gonna flip the signs here. If it's given in negative sign, if it's released, it's going to be taken by flipping the signs. If you want to flip it, just you're gonna turn the charges. So, right now we are going to calculate heat of that given reaction by using 2 steps or two reaction. Equation number 1, the second one, equation number 2. By referring to this equation, we are going to find S in solid state by the given equations. Where could we find it? Actually, it's in the first equation, and it is similar exactly, 1-to-1 coefficient, and they both are at the solid state, so that keep it in your mind, we may use the first equation with no changes. Oxygen are here also. SO2, where could we find it? SO2, here it's in reactant side, and it is needed to be in product side. I feel like we should flip it. If we want to flip it, this sign going to be converted to positive. The first point, what about the coefficients? Here it is 2, here is 1. So this equation, it could be treated in a certain way in order to make it like what do we need here. So that how could we treat it? We may say that equation 2, it could be divided by 2. Like the first component, if it's divided by 2, it's turned to S2 as a gas, plus the 1 mole of O2s, it's going to be half mole if it's divided by O2 as a gas. The last component here, 2 as O3, it's turned to SO3 just if it's divided by 2. Is enthalpy of that reaction could be changed? For sure, enthalpy, it's a component of this reaction. And also you had to divide it by 2. So 198 by long division, it's going to be divided by 2. So 19 divided by 2, it's 9, 18 here, 1, 8, 9, 18.2, so simply it's 0.1, negative 99.1 kilojoule. That's the long division. First point, we divide it. Is it ready to be used? Actually not. It should be flipped. So flip it. Flip it. How could we flip it? SO3 as a gaseous state, here. SO3 as a gaseous state, it's turned to, it was here like as a product, and it's turned to reactant here. SO2, the target, it's turned to product side, SO2 2 as a gas plus half of O2 like a gas. Have we finished here, guys? We could write it as equation number 3. Okay, could we add equation number 3 to equation number 2 in order to find this target? Is it ready to be used? Let us write it over it to find, can we cancel the repetitions or not? Over the arrow here, write the arrow there. SO3, the lonely component of reactants, and copy it there if you please. SO2 in a gaseous state and half of O2 in a gaseous state. The heat of this reaction, by flipping its turn to, heat of this reaction is positive 99.1 kilojoule. Okay, here we have. Could we erase this equation, equation 2, and try to add it to each other's? We took it previously. If there is something repeated at both sides of equations, simply it could be cancelled. If there isn't, keep it. First of all, guys, here SO3 and SO3, same amount, same component, at opposite side, it's going to be cancelled. What's left up in that side? In that side here, there is S in solid state added to 3 over 2 O2 in gaseous state, producing, here it's cancelled. What's left up? SO2, and it's our target here, plus half of O2 as a gas. What's going to happen to those? Actually add them to each other's, because we added the both equations. So 99.1 in a positive state, and it's 395.2 negative 296.1. So keep it in your mind. Here delta H, it's equal to 296.1, and it's negative joule. Okay, have we finished? Actually not. We didn't reach the target. Why? Because here S with S, SO2 with SO2, but O2, it's not there. Could we cancel those with each other's? Could we abbreviate it at both sides? Actually it is. Here half, here 3/2. If we remove those, if we cancel those, oxygen here is cancelled, and what's left up? Like 3 over 2 minus 1 over 2. What's the answer? The answer is 2 over 2. After taking that amount of the both sides, what's left up here is just 1 O2. So that cancelling here, it's turned to 2 over 2, means 1. So the final answer is S in a solid state plus O2 in a gaseous state, producing SO2 in a gaseous state, and the change of heat, it's equal to negative 6.1 kilojoule, and that is the needed answer. Hess's law, another practice. The target to find out the heat of this equation by referring to multi-steps reactions given previously in those three equations. First target here, 2C at solid state. Where could we find it? Actually, it's at the middle. If it's at the middle, it should be turned to this equation to 2, because the target is 2C. Here is just C. So the whole equation, it's going to multiply by 2. Let us prepare it first of all and keep the arrow here at the middle. The first one here, it's 2. This equation is multiplied, like what's mentioned, by 2. The another component, oxygen, if it's multiplied by 2, it's turned to 2O2 as a gas. The last component, it's 2CO2, like a gas. And also, delta H, enthalpy, it's going to multiply by 2 here. So it's 8, 18, 7. It's turned to negative 788 kilojoule. The first component is prepared. The second component, from where we could get it, from which equation? Actually, it's in the third equation, and it's already ready to be used. Why? Because it's 1-to-1 coefficient, and that is our target. So just copy the another equation without any changes, the arrow here, and it's H2 in a gaseous state plus half of O2 in a gaseous state. It's H2O liquid, and enthalpy as it is gas, which is negative 286 kilojoule. The final product, and it's at product side here, there it's at reactant side. What should we do? We said that you're just gonna flip it without any multiplications because it's 1-to-1 here. So just flip it to make it ready to use. The last equations, this equation, it's going to be flipped. Keep the arrow at the middle, make the product like reactants without any changes of coefficients, plus H2O as a liquid, and the another side, it's C2, H2 as a gas, plus 5/2 O2, and delta H, it's turned to positive 1,300 kilojoule. Right now, add all of those reactants with themselves, products with themselves, and cancel the repetitions if there is. Add those to each others in order to find out your target if it is matched this equation. Let us find if there is something could be cancelled. First of all, guys, CO2 here, CO2 there, 2CO2, 2CO2, it's going to be cancelled. What else? How many H2Os? Here 1, and there is here 1, and those going to be cancelled. What else? Here is O2O2, and here is half O2. Could we add them to each other's? 2 plus half, it's equal to it. Here it's 1 multiplied by 2 multiplied by 2, it's turned to 4/2. 4/2 plus 1, it means 5/2. So those, when those are combined to each others, those, it turns to 5/2 O2. And here is 5/2 O2, so that those with this oxygen, it's going to be cancelled. What's left up, guys? What's left up in reactant side, it's 2 carbon in solid state added to H2 in a gaseous state, and everything here is cancelled. In product side, cancelled, 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 and C2, H2 in a gaseous state. And I think this equation matches the target, so that the combination of those enthalpies 2, 6. The greater is the positive as kilojoule. And that is it.